Okay, so let's talk about the binomial theorem, which is the theorem where the term binomial coefficients comes from. Right, so remember this refers to this notation, n choose k, which arises when we compute the number of combinations of n things taken k at a time. Right, so it's n factorial over k factorial times n minus k factorial. Now, to see why, let's look at a few small examples. So let's consider the binomial x plus y and look at its powers for small exponents. X plus y to the first power, well, that's just x plus y. Right, so there's one term here with x and one term with y. So there's nothing really interesting there. Let's look at the next one. When you compute x plus y squared, well, from grade school or middle school, you probably remember this formula, x squared plus 2xy plus y squared. But remember that this formula comes from simply multiplying these terms out. You get x times x, x times y times x, and y times y. Right? And so you have two terms that are really the same term here, x times y, and that's why we have 2xy in the middle. But now notice what we were doing here. Observe that really we were forming these strings of length 2 that are composed of either x or y. Right, so you can have 2 x's, 2 y's, or 1 x and 1 y. And sure enough, if we count the number of such strings that are composed of exactly 2 x's, well, that's exactly equal to 2 choose 2, or 2 choose 0, depending on whether you're counting the x's or the y's. Similarly, if you look at the two middle terms, you see here that 2 is equal to 2 choose 1, which you can view here as, given 2 spaces, how many ways are there to pick a space to put an x in? So we can either put the x in the first space, in which case we get a y in the second, or we can put an x in the second space, in which case we get a y in the first. So there are 2 ways, and that's why we get 2xy here. And finally, for the last term, it's also 2 choose 2, which is the same thing as 2 choose 0, right? So it's symmetric. Because given 2 spaces, you're either picking 0 of them in which to put x's, or 2 of them in which to put y's. Right, so that's how the binomial coefficients appear in this small example. And in fact, if you continue and look at the cube of x plus y, you'll see the same pattern. Because now, well, first I'll write down what you probably remember. It's x cubed plus 3x squared y plus 3xy squared plus y cubed. Now the question is, we have 3 spaces, right? We're forming a string of length 3 consisting of only x's or y's. How many ways are there to complete this string using only x's? Well, there's only one way, and that is to pick all 3 of the spaces to be x's. So 3 choose 3 is the coefficient of x cubed. Now, how many ways are there to fill the spaces with 2 x's and 1 y? We can have an xxy, xyx, or a yxx, giving us 3 choose 2 terms, or 3 choose 2 strings that all correspond to x squared y. And so on. So this is 3 choose 1 and 3 choose 0 for the coefficients of xy squared and y cubed. Right, so again, the reason why this is equivalent to forming these strings is because when you're multiplying x plus y by itself 3 times, because of this distribution that you're doing, every term in the result, right, in the resulting sum is going to be a combination of 1 from the first binomial, 1 from the second, and 1 from the third. Right, so x cubed corresponds to picking x for each one. X squared y, you can pick x, x, y, x, y, x, or y, x, x. And that's where we get this formula. And you can verify it for yourself for the fourth power. The coefficients there are 1, 4, 6, 4, and 1, where the coefficients follow the same pattern. You start with x to the fourth power, then you take 3 x's and 1 y, then 2 of each, then 1 x and 3 y's, and then finally 4 y's. Right, and to be sure, these are exactly the binomial coefficients 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And so we now have an idea of what happens for the general case. If we follow the same pattern, and imagine that we're picking either x or y from each of these n terms, well, that means to get x to the nth power, we only have one way, which is to pick x's for everything. So that's 1, or and choose n. Right, so from n of these terms, we're picking n x's. How about the next term, which is x to the n minus 1 times y? Right, so if we pick 1y and n minus 1 x's, how many ways are there to do so? Well, now it's n, choose n minus 1. Right, so among these n terms, let's pick n minus 1 of them to give us x's. And so on and so forth. And this is basically the proof of the binomial theorem, which says that the coefficient of x raised to n minus k times y to k, right? So if we pick n minus k x's and k y's, then the coefficient is n choose k. Right? Or you can also say the coefficient is n choose n minus k. Right? Again, these binomial coefficients are symmetric because of their formula. And so a nice application of this theorem is, well, now we can actually use it to compute any coefficient in such a binomial expansion. In fact, even when it's not just x or y that's inside. Right? So, in fact, this formula holds if you replace x by something else. You just have to replace that x into this formula inside the summation notation. Right, so let's end with a few examples here. Well, the first example here is pretty standard. It's x plus y to the 9th power. Right, so it's n equals 9 here, which is the power of the binomial. And you're looking for the coefficient of x to the 6th times y cubed. And again, from the previous argument, we know that's going to be 9 choose 3 or 9 choose 6. Simply because x to the 6th times y cubed corresponds to forming strings of 6 x's and 3 y's. Right? So how many ways are there to pick 6 of these terms in the product to form your x's? Exactly 9 choose 6. Right? So this is exactly by the binomial theorem. Now for the second example, here's one example where we replace x and y by something else. Now we have 3x plus 2y inside the sum. So the binomial theorem says this expansion is equal to summation k equals 0 to n, and choose k. Right, so a while ago it was x raised to n minus k, y raised to k inside the summation. But now our x here, in quotations, is this 3x term. And our y here, in quotations, is this 2y term. Moreover, let's just plug in 9 for n. And this is now the expansion of this binomial raised to the 9th power. In which case, the coefficient of x to the 6th times y cubed, well, to determine that, first you just have to determine which index k it corresponds to. Right, so it corresponds to index k equals 3, because that gives you a power of 6 for x and 3 for y. So the term corresponding to k equals 3 in the summation is equal to 9, choose 3, right? Just plug in 3 for k. 3x 9 minus 3. And then 2y raised to 3. And simplifying, now this is 3 to the 6th power times x to the 6th, 2 cubed times y cubed. Therefore, the coefficient is 9 choose 3 times 3 to the 6th times 2 cubed. And so this whole term here is what we're looking for. And that's the coefficient.